Our last topic for this chapter, we're going to be talking about forced oscillations and resonance. So we've been looking at differential equations in this chapter that were homogeneous, meaning that we had some equation when we had a second order. We talked about friction, and we had some property of the spring or pendulum or whatever system, and that was equal to 0. And this, of course, we know this is the homogeneous differential equation, but it also describes the natural internal response to the system from itself. So it's just all the internal forces, all the internal reactions, nothing from the outside is affecting it. But we can also add a forcing function to this. And that would be put on the right hand side, some function f of t. And now this is the non-homogeneous and it's going to include the natural response plus the response to the external force. So we always looked at solutions coming in two parts. You had the x of the homogeneous the x function in a homogeneous solution plus the x of the non-homogeneous solution. And now we can equate that to something that will make some sense as to what it actually represents. We can call this homogeneous part the natural response, how the system reacts to itself, plus the non-homogeneous solution is going to be the forced reaction. Now, this is quite useful because there are situations where things can get out of hand. So let's look at our functions before. I created a little simulation in MathCAD. I've got the formula that we just talked about. I'm having it do a solve. So it's doing a numerical solution. And okay, it's not going to do it, but go back anymore. So Here I have set for just straight oscillations, and it's undamped. Now we can come up with a value of omega very quickly here. It's just the square root of k over m. This k of the spring over m, and take the square root. Well, 2 over 2 is 1. Take the square root is 1. So I can create a forcing function. Right now I have the amplitude set at 0, so in effect there is no force in that function, in that equation. But watch what happens when I put a value of 1 into my forcing function for the amplitude. You'll notice that the waveform is growing without bound. And this is the property called resonance. When the forcing function has the same period as the system's natural internal response, it produces this out of control situation. Not a good thing to have, because this means that something's going to break. Now, if I want to control this, what I can do is I can start adding in a little bit of friction. So let's start with 0.1. Let's see what happens there if I add just a little bit of friction. Well, it's still going higher without bound, so we can add a little bit more. And still, it's coming down, but it's still pretty high. Let's crank it up. Let's put this to 1. Well, that's pretty good. We've seen that now it's becoming a little more stable. Now the amplitude has increased. We had started it out at 1 centimeter, and now we're to 1 meter. But that 1 meter looks pretty solid. Doesn't look like it's growing much more. Let's kick it up just a little bit more. And that looks even better. So now I'm controlling the system by putting friction into it. Now this is kind of an odd thing to do, because we'd think, well, if I'm putting in friction, I'm wasting energy. But by wasting energy, we control the system so that it doesn't blow apart, so to speak. And this is the idea of forced oscillations and control. How can I control the system so that it doesn't break? Now, we can increase this up quite a bit higher. Put the friction constant right up there. And now you can see with a high friction, it's just responding to the value of the forcing function. And it's staying pretty close to 10 centimeters. What happens if I make this critically damped? There you see that it's very stable. This is the best possible solution, because here, because it's critically damped, the system wants to remain stable. It wants to go to 0 as fast as possible, but the oscillation will keep it moving continuously, but the critically damped will maintain the peaks at the same level. So it becomes very important when you're designing a system that everything is controlled, and we control it by this friction coefficient. What happens if our forcing function is not in the resonance frequency? So let's change this friction back to 0, and let's put in a different omega value. And now you can see that you have the forced function superimposed onto the natural response, the unnatural undamped response of the system. And just to prove that that is so, let's put it up even higher. And you can see how it still has the undamped response, but the forced is superimposed on top of it. This is a very interesting phenomena, a very interesting subject. There are classes that are strictly looking at how to control systems based on these different parameters. It's called controls. It's a very interesting class if you're ever wanting to get into this type of work. It's looking at how you design systems so that they're most efficient and not going into an unstable mode.